Okay, check this out. So turn the camera off. When the camera's off, that means it's a TLDR, too long didn't read version of the video that I just did. If you really can't bring yourself to watch the video or you need to go back and refresh, you should watch this one at the very, very, very least. This part of the course is the most difficult. So oftentimes you're going to forget things I've said that are super important. So these videos are going to be designed to be way faster. I'm already going to use the notes I've already generated from the first video, and I'm just going to quickly highlight the things you should know how to do. I strongly suggest you still watch the other lessons. I don't even know how I'm going to post these yet. This is just me starting to create this. So we'll play it by ear. But here we go. Here's the first one. So we're talking about sequences. I said in the other video, I won't keep saying that, but a sequence is just a list of numbers generated by a mathematical rule. So you can see 1, 2, 4, 8, 16. That is a sequence of numbers that are generated by doubling the previous number, basically. Here's a formula for generating it, though. The notation A means the sequence is called A, and the subscript N is the number of the sequence. So to get the first number of the sequence, you plug in 1 for N, and you would get 1. To get the second number of the sequence, you'd plug in 2, and you'd get the second number of the sequence, which is 2. To get the fifth number of the sequence, you'd plug in 5, and you get 2 to the fourth, which is 16. So we can generate a sequence using this, which is called the explicit formula for the sequence. Okay, so here are some examples of sequences. Here's one that when I plug in 1, 2, 3, 4, whatever, I get the sequence 2, 4, 2, 4, 2, 4, which alternates. We'll talk about these in a second. This is a cool sequence that alternates back and forth between terms. If I plugged in to the next one, I would get the sequence 3, 9, 27, 81, 243. By the way, this process is called expanding out the sequence. And in the other one, same thing. When I plug in 1, 2, 3, I get this sequence right here. So the point of what we are trying to do in this section really is just to determine if a sequence converges to a value or diverges. And when I say converges to a value, I mean, does it get closer and closer to a last term? So the first one does not. We bounce back and forth between 2 and 4. We never get closer and closer to a final term. We're always 2 or 4 or 2 or 4 or 2 or 4. This infinite sequence never gets closer to a value. The next one gets bigger and bigger and bigger, but never gets closer to a value. So in this case, this one also diverges. It's the last one that, if you notice, we're getting closer and closer to 0. So this sequence converges to 0. Every term is getting closer and closer and closer to 0. The quote-unquote last term would be 0. All right, so here's another example. We have this sequence, which I wrote the first few terms of the sequence and generated it. And I'm asking, does this converge or diverge? It's not easy to tell because you're like, well, it's getting bigger and bigger and bigger, except it is not getting bigger and bigger forever. It's bounded above by a number. And then what it is bounded by, aka the last term, aka what it converges to, is 3. How did I do that so quickly? Well, really, at the end of the day, we're just talking about the end behavior. So what a sequence converges to is simply the end behavior of that sequence if we were to look at it like a function. And to find the end behavior of a function like this, we know by now that if the powers are the same, we can just divide the leading coefficients and we get 3. So in this case, we have this sequence. I don't even need to generate or expand out the sequence. I can just use the end behavior and look at it again. I have the same power top and bottom. So divide the coefficients, I would get -1/2. Cool, not so bad. It's a little worse when you have a mix of functions. So in this case, we have n plus 1 on the top and 3 to the n on the bottom. Well, what's going on here? The top's growing, but the bottom is growing, keyword faster. So if the bottom function is faster growing than the top function, that means the entire sequence goes to 0 or converges to 0. And a lot of times we'll either get 0 or diverges for this situation when we have a mix of functions. So that is then the important part of this next thing where we need to talk about the growth rate of functions and how they compare. Log functions are the slowest growing. The bigger the base, the slower growing it is. A natural log is just a type of log function. It's a log base e, or in other words, log base 2.718. And it is one of the slowest growing functions we have. So log base 10 is slower growing than log base 3, which is slower growing than natural log, slower growing than log base 2, and so on. Faster growing is radicals. The bigger the base, the slower growing. So 10th roots are slower than cube roots, slower than square roots. Next is linear. We only have one linear. Remember, coefficients don't affect overall growth rate. So at infinity, and that's what I talk about in this next part, a coefficient's not going to change growth rate. So not exactly. It's going to affect the end behavior, but it's not going to affect like 2n squared and 7n squared. Both grow by a factor of n squared. This one is just 7 times bigger than this one at every point. Not super important. Just it's our end behavior rules. When we have the same power, they have the same growth rate. So N squared is slower growing than n cubed. The bigger the power, the faster it's growing. Exponentials. 2 to the n is slower growing than e to the n is slower growing than 5 to the n. So don't look at these like coefficients. These are part of the function. 2 to the n, the base being 2, is slower growing than 5 to the n. So if you had 2 to the n over 5 to the n, that converges to 0 because the bottom is slower growing than the top. Okay, so I will actually rewrite that because that is one of the things that's going to confuse you. So this versus, let's say something like 2n squared over 5n squared. 2 to the n over 5 to the n, this converges to 0 because the top is slower growing than the bottom. This, the same growth rate, these are coefficients, not part of the function. So this converges to 2/5. 2/5, 0. And finally, we have this thing called a factorial, and the factorial is the fastest growing function we're going to be dealing with. Technically, yeah, there's this other one, n to the n, and then combinations, but we're not going to see this a lot. N factorial is the fastest growing. What is a factorial? A factorial is just a number times all the subsequent numbers less than it that are whole numbers. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So factorial is the fastest growing. So if I give you a problem like this, n factorial over 200 to the n, you just got to look at it, no work to show, and say, oh, n factorial is way faster growing than 200 to the n, which means that this diverges. This sequence diverges. And then I did a little comparison here that, because you may think, well, if I plug in 1 over 200, and I plug in 2, I get 2 over 200 squared. It looks like it's going to 0, but in infinity, n factorial is bigger than 200 to the infinity. Like, factorial is the fastest growing function, so you just got to know that. Lastly, when you see cosine or sine of n, cosine of n does not grow. Cosine of n fluctuates between -1 and 1, bounces back and forth, back and forth, back and forth. So really, a cheat for this class that we can get away with is just saying, oh, this is like 1 over n, because cosine n does not grow, n is n, so this converges to 0. So anytime you see a cosine n or sine of n, you can almost just cancel it out and rewrite it as a 1. And lastly, we're going to see negative exponents a lot. Don't let them trip you up. Just move them to the denominator to create fractions and then compare growth rates. All right, that's it. 7-minute video, not bad. I kind of like this.